Hi, I'm Patty Schwarzkopf. Today I'm meeting with one of my students to talk about linear functions, slope, and applications. We'll begin by determining the slope of a line given 2 points on the line. Then we'll solve applied problems involving linear functions. We can often use a mathematical model to describe real-life situations. One type of mathematical model is a linear model. To get to that, we'll first look at linear graphs. These first two graphs are representative of linear functions. We have a straight line defined by y equals x plus 2 and a straight line defined by y equals 2. Again, these two describe linear functions. These two graphs do not describe linear functions. We can see that their graphs are not straight lines. You can recognize a linear function from its form, from its equation. A function f is a linear function if it can be written as f of x equals mx plus b, where m and b are constants. Let's take a look at a few graphs. We have f of x equals 2/3 x minus 3 and f of x equals negative 3. Both of these describe linear functions. And we can see that the graphs of each of these functions is a straight line. Now the graph of the third equation is a straight line, but it is not representative of a function because it does not pass the vertical line test. So this is a linear equation, but it's not a linear function. Now, although every graph of a linear function is a straight line, the lines differ in where they are positioned on the Cartesian plane and in their steepness or slope. The slope of a line is a measure of how it rises in proportion to a fixed horizontal distance. We can calculate the slope of a line if we know 2 points on the line. To calculate the slope, we'll use the following formula. The slope m of a line containing points x sub 1, y sub 1, and x sub 2, y sub 2 is given by m equals y sub 2 minus y sub 1 over x sub 2 minus x sub 1. Sometimes you've seen this as rise over run, or the change in y over the change in x. Let's take a look at an example. Find the slope of the line containing the points 4, negative 9, and negative 5, 6. Now, remember that we have slope equals rise over run, so that's a change in y over the change in x. So what numbers do we subtract in the numerator?
The numerator is the rise, so we should subtract the y-coordinates.
That's right.
Do we subtract negative 9 minus 6 or 6 minus negative 9?
Well, that's a good question. It actually doesn't matter which point you call the first point and which point you call the second point. It just is very important for you to be consistent. So if in the numerator you subtract negative 9 minus 6, then in the denominator you will need to subtract 4 minus negative 5. If, on the other hand, in the numerator you decided to subtract 6 minus negative 9, then in the denominator you need to start with negative 5 in the subtraction. It would be negative 5 minus 4. So let's work it both ways and see what happens. We have the slope of negative 9 minus 6 as negative 9 minus 6 in the numerator over 4 minus negative 5 in the denominator. So the slope equals negative 15 over 9, or negative 15 ninths. And we can simplify that. That would be negative 5/3. Now let's work it the other way. In the numerator, instead of subtracting negative 9 minus 6, I'll do it this way. I'll subtract positive 6 minus negative 9. So we have 6 minus negative 9 in the numerator over negative 5 minus 4. So we have the slope equals positive 15 over negative 9. So the slope equals negative 15 ninths. And if we simplify that, we have negative 5/3 again. So you can see that the order was not important. What was very important is that you remain consistent. Now, if a function is written in the form f of x equals mx plus b, we can read directly from that form the slope or the steepness and the point at which the line crosses the y-axis or the y-intercept. Let's see. The slope of the line given by y equals mx plus b is m. In other words, the coefficient of x. The slope of a horizontal line given by y equals b is 0. The slope of a vertical line given by x equals a is not defined. Now notice here, y equals b, this represents a horizontal line, and again, the slope of a horizontal line is 0. X equals a constant is the form for a vertical line, and vertical lines have slopes that are not defined. So we'll determine the slope of each of the following lines. We have y equals 1/2 x minus 3, y equals -2, and x equals 7. Now, the first equation is written in the form y equals mx plus b. What is the slope?
The slope is 1/2.
Right. So slope is 1/2. Now, the equation y equals -2 is a horizontal line. So what is the slope?
0.
Good. And x equals 7 is the equation of a vertical line. What is the slope?
It's not defined.
Good. Now the slope and linear functions have many applications. Let's take a look at one. Construction laws regarding access ramps for the handicapped state that every rise of 1 foot requires a horizontal run of 12 feet. What is the grade or slope of such a ramp? Now, the grade or slope is expressed in how much the ramp rises for a horizontal run of 100 feet. So in other words, we're looking for the percent here. Now, when we look at the slope, remember that we're looking at the vertical change over the horizontal change. So the vertical change is 1 foot over the horizontal change, which is 12 feet. So we have that is approximately 0.083, which is approximately 8.3%. So the grade is an 8.3% grade. Let's take a look at another problem. An Olympic marathoner passes the 10-kilometer point of a race after 50 minutes and arrives at the 25-kilometer point 1.5 hours later. Find the speed, the average rate of change of the runner. Now the average rate of change is denoted by the slope. So all we need to do is to determine 2 points from this, and then we can determine the slope. So what I'll do is write the first piece of information using an ordered pair. We know at 50 minutes the marathoner was at the 10-kilometer point. So we have an ordered pair, 50, 10. And we also know that 1.5 hours later, or 90 minutes after running 50 minutes, the marathoner was at the 25-kilometer point. So 90 minutes after 50 minutes is 140, and the marathoner was at the 25-kilometer. So at 50 minutes, the marathoner was at the 10-kilometer point, and after 140 minutes, the marathoner was at the 25-kilometer point. So all we need to do now is to determine the slope, and then we'll have the average rate of change. So we have m equals 25 minus 10 over 140 minus 50. So the slope equals 15 over 90, which equals 1/6 kilometers per minute. Let's take a look at another example. Suppose that while driving a car, you suddenly see a school crossing guard standing in the road. Your brain registers the information and sends a signal to your foot to hit the brake. The car travels a distance d in feet during this time, where d is a function of the speed, r, in miles per hour, that the car is traveling when you see the crossing guard. The reaction distance is given by the linear function d of r equals 11r plus 5 over 10. First, we'll find the slope of this line and interpret its meaning in this application. Well, remember that we can read the slope if we can get this in the form f of x equals mx plus b, or in this case, d of r equals m times r plus b. So I'll rewrite this as d of r equals 11/10 r plus 5/10, or d of r equals 11/10 r plus 1/2. So the slope here is 11/10. Now, in d of r, r is in miles per hour and d is in feet. What would the slope of 11/10 mean in this application?
Well, for every horizontal change of 10 units, there's a vertical change of 11. That would mean that for every 10 miles per hour increase in the speed of the car, there would be an increase of 11 feet in the reaction distance.
Very good, very good. For every 10 mile per hour increase in the speed of the car, there's an increase of 11 feet in the reaction distance. And that's how we interpret the slope. Let's answer a couple more questions regarding this application. Again, we have d of r equals 11r plus 5 over 10. Let's find the following. We have d of 5, d of 10, d of 20, d of 50, and d of 65. d of 5 equals 11 times 5 plus 5 over 10, which equals 55 plus 5 over 10, or 60 over 10, which is 6. Okay, and that's in feet. d of 10 is 11 times 10 plus 5 over 10, so it's 110 plus 5 over 10, or 115 over 10, which is 11.5 feet. d of 20 is 11 times 20 plus 5 over 10, so we have 220 plus 5 over 10, which equals 225 over 10, or 22.5 feet. d of 50 is 11 times 50 plus 5 over 10, so we have 550 plus 5 over 10, that's 555 over 10, or 55.5 feet. And d of 65 is 11 times 65 plus 5 over 10, so that equals 715 plus 5 over 10, or 720 over 10, and that's 72 feet. And finally, what is the domain of this function? Now, the domain of a function is often determined by the application. Now, in this case, a negative speed doesn't make sense. So, nor is there any stopping distance when the car is not moving at all. So the domain is from 0 to infinity. In other words, we're only looking at speeds that are greater than 0. Now, today we looked at linear functions, and especially at the slope of a line. Make sure to review all that we've talked about today before you begin the exercise set. And if you're having any trouble, make sure to see your instructor for help.